Hello and welcome to the fourth lesson on energy. We're talking about thermal energy and heat today. The learning goal is that I can explain the concepts of thermal energy and heat and make the appropriate calculations. So, before we get into the calculation part, let's talk about the kinetic molecular theory. So the kinetic molecular theory. And it's the current theory that's used to understand how atomic theory and related materials interact. So you'll come across this if you take a chemistry class. There are three main postulates, and a postulate is really just best guess. All right, we can't prove it factually, but it's what we're running with right now to help us continue with our research. So the first one is that all matter is made up of small moving particles called atoms, and when atoms join together, they form what we call molecules. Atoms or molecules exert forces on each other. So that means that they have pushes and pulls on each other. And remember, if a molecule is made up of particles, there's negatively charged, positively charged, so they either attract or repel each other. All right. And the third one, the distance between the molecules and strength of force between them is responsible for our three states of matter. So I'm going to talk about that and give you an analogy to tie that together so you can better understand it. So in this diagram, I'm just going to fill in what I'd call, just something to allow you to visualize what we're talking about. So our three states of matter are solid, liquid, and gas. All right. And what do each of these look like? Well, we know solid is a very rigid structure. So I'm going to make a cube. So if you follow me along here, so make a matrix of dots like that, and then we're going to put 3 dots across the back, and then we got to kind of go down inside here. And what we're going to do is we're going to make a 3D object. So I'm going to connect the outside of my box, just like that, and then the back will connect. All right, so there we go. And now what we're going to do, and maybe it's just as easy for you to draw across the middle here. All right, because what we're going to talk about are these bonds. Oops. All right, and what happens is these molecules form a rigid box. Okay, a very rigid box. And that's why it's allowed to stay and maintain its form. So if I was to take the class and I tie students together, using steel rods. So if I was to connect to your belt a steel rod, and I connected the other end to another student, and so on and so forth, to link you all together, all right, if those red bars represented steel bars, if I asked you to move, you would have to move as an entire group together. You'd be locked together in the square or triangle or whatever form I gave you. All right, so if I had student A, student B, and student C, and I put these steel bars in like that, you would have to maintain that triangular shape because you are locked together. All right, and that's how a rigid works with those molecules that's close enough together that the push or pull is just that strong. Now with a liquid, what happens is those bonds are loosened. So instead of rigid rods, I'm going to use the notation for a spring here. So if you draw a couple dots, connect them with squiggly lines, they represent springs. All right, it looked like that, something like that anyway. You'd have a whole bunch of springs connecting them. All right, so that would mean that, okay, instead of using the steel rods, I would take all the students and I'd tie them together using bungee cords. All right, so those bungee cords are now flexible. So now that triangle that I had originally, if I replace those steel rods with bungee cords, you can now distort the shape and you could stretch that one bungee cord pretty tight, so you don't have to maintain that rigid shape. Now you're allowed to change and be fluid or liquid. Okay, so you're allowed to morph your shape according to the situation. And finally, gas particles are such that they get spread out and the bonds aren't even touching or connected anymore. All right, they're able to dissipate. All right, so I'm just drawing some red lines to show there's a little bit of push and pull, but not enough to maintain the shape. All right, so this would be take students outside and turn my back. If I was to take you outside, turn around, cover my eyes, i.e., you would run away and go home. All right, so there's nothing holding you or linking you. Okay, you can spread out and you can head off in your own directions. You'd be gone. Okay, so there are your three states and kind of the reasons why or how those bonds work. So conductor versus insulator. We have the two types. We hear it in electricity as well. So conductor versus insulator. Definition here. Conductor readily transfers heat, energy, and an example would be steel. So if you're out roasting marshmallows with a clothes hanger, you got to be a little bit careful. That heat energy will transfer up the length of the clothes hanger. If you have an insulator, it does not readily transfer heat energy. All right, and some examples, i.e., okay, air is a good example of an insulator. It doesn't transfer heat energy efficiently. It'll transfer a little bit, but not efficiently. Okay, three types of heat transfers. So how does heat transfer from one to the other? So conduction is the process of transferring heat by particle collisions. Okay, so basically I got a couple of examples. The old stove cooktop. All right, and if you ever take a look at your stove, some of the old ones have the spiral element. Okay, so what happens is we have a resistor here, so it changes the electrical energy to heat energy, and that heat energy then begins to circulate around the rod until it reaches the middle. Okay, and that's one of the reasons why those old cooktops are not preferable, because when we're talking about the heat, the hot area tends to be outside. Oops, and then in here, in the middle here, it takes the longest for the heat energy to get there. So that's why the center doesn't always cook properly on the pancake if you're using the old stove. So it's one example of a transfer. And I already talked about the other one, clothes hanger for roasting. All right, so if you've got your fire going, these are logs, by the way, you can talk. We got our fire, and we got you standing here holding the rod, make it a green marshmallow. What happens is that steel rod heats up and it moves up toward your hands and can potentially burn them. All right, so there's the first type of heat transfer, is the old conduction method. Next one we're looking at is convection. So we did conduction, convection, the process of transferring heat by circulating path of fluid. Now, most people don't realize that air is a form of fluid. So in your house, all right, some of you will have maybe a wood stove or a register. All right, so down here, the heat register. All right, so what happens, the heat is generated in this corner. What happens to warm air? Well, warm air rises. All right, so in your house, warm air will rise in that stage right there. At the top of the stage here, it kind of changes to blue because your air cools. All right, so the air begins to cool, and then cold air falls. Cold air falls or takes the place that's evacuated by the warm air. And what happens is you have this cycle inside your house then. So hot air rises, cool air then falls back down to take its place and gets heated, and you get that continual system. And that's why you see a lot of places, or why it's necessary. It's necessary to install a ceiling fan. The ceiling fan will push that hot air back down and heat that ground floor. So if you just have a wood stove in the house, you'll find that the upstairs of your house is always very, very hot. And the reason for that is because all that warm air is rising up. Another example is the seashore. Why is there a breeze? So here's the seashore. Here's you. You're blue. Here's my water. So what happens is that the sun here, sun heats the sand. Then heats air. So that sand is really hot on your feet. So that air gets hot and rises. What happens then is that we have cold air rush in to fill that void. So cool air rushes in. But what happens, because the cool air has evacuated this region right here, so the cool air is moved, it draws that hot air over here. All right? But what happens at the high altitude? At high altitude, air cools. So if it cools, it then falls down, and the cycle repeats. So that's why it's often that you have a breeze at the beach. If the sun is out, it's heating up the air on the beach, causing that warm air to disappear, then sucking the cool air off the lake and in. All right. And the third and final one we're talking about is radiation. So radiation is a transfer of heat energy through electromagnetic radiant energy. So electromagnetic waves. And yes, that is a term that you will need to be familiar with. So with it, heat lamps, if you've ever been in a pig barn, or if you ever go to the old style restaurants, McDonald's, or sometimes if they have the old style buffet tables, they have red lights. So we'll do it in red. Over your food, red light creates these electromagnetic waves, which excites the food. All right, so if I have a blue turkey down here, okay, it will excite the atoms to make them move, excite the molecules, and that excitation creates heat or keeps the food warm. Similarly with a microwave oven, we have large magnets with electric energy in there, and inside that microwave, again, I'll draw my blue turkey. Everyone likes a blue turkey. These magnets create electromagnetic waves throughout. And those electromagnetic waves, when they strike a solid, all right, then they excite the molecules that make up the food, and those excited molecules vibrate, therefore creating heat. So magnets create electromagnetic waves. All right, so that's kind of the theory component. The second part of the video, I got to do the lesson in two parts, will be the mathematical end of it.